Hello everyone. Well, thus far in this lecture series we have covered the basics of the Python language. That being the basic data types, the scalars and collections, the if clause, and the for and while loops. So now we're ready to introduce our first third-party package, and that's going to be NumPy. So why NumPy? Well, NumPy is essential for any sort of numerical computation. Yes, we have looked at the math package from the standard library, but that is best suited for small calculator type calculations. But frankly, when we as engineers and scientists come to a computer, we are really looking to do something bigger. We're looking to do calculations with large numbers of numbers or even large data sets. And that's where NumPy is going to shine. So let me motivate it with a quick example. Recall this code that we wrote in a previous video. This is where we wanted to calculate the areas of various circles of different radius. And so we started by putting these radiuses into a Python list and then iterating through that list with a for loop, and within the for loop calculating the area corresponding to each radius and then storing those in another list. So now compare that to the analogous code written using NumPy. Here it is. It begins by importing NumPy. This is just a standard line that brings in all of the functionality of the NumPy package, and it's conventional to abbreviate NumPy with NP. So wherever you see NP, it's referring to NumPy. When we do this with NumPy, instead of defining a list, we're going to define a so-called NumPy array, or just array. We'll just call it an array. And once you have the data in an array, you see that the calculation of the areas is just a one-liner. Okay, so NumPy is going to know that when you take the square of an array, something that you could not do with the list, what you mean is you want to take the square of each element in the array. And then when you multiply by a constant, pi, and notice that here we're getting our pi from NumPy itself, that means multiplying by each element in the array. And so it gives us a very nice syntax for a calculation. And what you'll notice is that once you learn how to code in NumPy, your calculations will become much easier to read. And in particular, you'll have much fewer for loops in your code. But the advantages aren't only aesthetic. NumPy arrays also offer benefits in terms of features that are more tangible, things like efficiency and functionality. I want to show you a couple of those. So lists, as you know, they are inhomogeneous, meaning that they can hold any assortment of different things. And so when you create a list, you usually create an empty list. And at that time, the list doesn't know what sorts of things are going to come at it, and so it cannot pre-allocate any memory. When you add an item to a list, such as this a musical note, it's going to add a reference to some where that item is stored in memory. And then the airplane may be a much smaller type of object, whereas a house, it could be a gigantic thing. And so yes, the list does not know a priori how to allocate memory, and so it will be very slow. A NumPy array, on the other hand, is homogeneous. It's made for numbers, so you can tell a NumPy array what types of numbers you're going to hold, whether they're going to be floats or integers or booleans. And it's also customary to actually pre-allocate the whole NumPy array with however many items you're going to need instead of growing it within a for loop like with a list. And so NumPy can then reserve a very orderly chunk of memory, and that will make it very, very fast as compared to a list. Also, lists are inherently one-dimensional, right? There's one thing coming after another in a sequence. That makes it a little bit difficult to model something like a matrix. And we as engineers use linear algebra so much that it is an important object to have. NumPy arrays, on the other hand, are inherently multidimensional. And that makes linear algebra work a lot better. So let me demonstrate that really quickly. Let's say that you want to define this matrix A that has 2 rows and 3 columns, and you want to do that using a list. Well, here's how you might do it. You create an empty list, and then you put as its first element the first row, and as its second element the second row. And so now you have the matrix defined as a list of lists. Okay, very good. But what's wrong here? The main thing that's wrong is that I could add another 7 there and Python wouldn't complain. Of course it wouldn't complain because I haven't violated any rules of lists. I've only violated a rule of math. And that rule is that a matrix must have a definite number of columns. And this one has 3 columns in the first row and 4 columns in the second row. So it's not a proper matrix. All right, without a definition or without a proper definition of a matrix, I won't, with lists, be able to implement all of the linear algebra operations like multiplying 2 matrices or taking the inverse of a matrix or the determinant or anything like that. So now let's see how NumPy is going to deal with this. We're going to import NumPy as NP, and I am going to take this very exact same code and I'm going to pass it into the constructor of NumPy arrays. And let's call that A and P. I get an error. And the error is essentially telling me that what I passed into the constructor was not a valid matrix. So NumPy is never going to give you an invalid matrix, and that's a good thing. Let's now try to, let's remove the 7, create a valid matrix, and see what it looks like. Well, we can see immediately that NumPy prints it more nicely than the lists did. That's because NumPy has already identified that this is a matrix-like object. Let's have a look at some of the data that's attached to this NumPy array object. First, we have the shape. And the shape is a tuple. It says it's 2 by 3. So from here we can know that, first of all, there are 2 dimensions because there are 2 entries in the shape. And we know that the first dimension has size 2, so there are 2 rows. And the second dimension has size 3. Because there are 3 columns. We can also know how many elements are in the array by looking at its size. And it tells us size is 6. And finally, we can know what type of numbers are stored in the array by looking at its D type. And it tells us that this array has 64-bit integers. If I had put .zeros here, then it would have detected that I'm passing floats, and the D type would be 64-bit float. Okay, so you can see that the NumPy array identifies and keeps a lot of information about whether it's a single-dimensional array or a matrix, or 3-dimensional would be a cube of numbers. You could have 4-dimensional, 5-dimensional, n-dimensional. And so that's going to make it a lot easier to work with. And over the next few videos, what we'll learn to do is to use all of the methods that get attached to an array or that are available through NumPy to make our numerical computations a lot faster and a lot easier to read and to code as well.